Next, to celebrate the 100th anniversary of the confirmation of Albert Einstein's general theory of relativity, acclaimed theoretical physicist, mathematician, and string theorist Brian Greene weaves together dramatic portrayals, stunning visuals, and innovative projection techniques to trace Einstein's journey toward one of the most beautiful ideas ever conceived.
This is Einstein's proposal for how gravity works.
With an ensemble cast and with words spoken by historical figures drawn from the archival record, Greene recounts the dramatic story of the breakthrough moments, near misses, agonizing frustrations, and final emergence into the light as one intrepid mind took on the universe and triumphed. Gaze into the heavens for a fascinating exploration of our world here on Earth. Light Falls is next.
Good evening. Thank you. Thank you very much. During the solar eclipse of May 29, 1919, two research teams took some of the most famous of all astronomical photographs. Photographs that are revered not for their beauty, but rather for the remarkable story they tell. Because those photographs, taken 100 years ago today, provided the first confirmation of Albert Einstein's most far-reaching discovery, the general theory of relativity. And with such a momentous anniversary upon us, I know that you all have been busily planning your own relativity parties and celebrations, which is great. So thank you all for taking time out from your own festivities to join us here tonight. Now, during my own celebratory preparations, I came upon a quote of Einstein's that I had never seen before. Einstein said that science is a wonderful thing if you don't have to earn your living at it. And it is always so gratifying when there's complete agreement between Albert Einstein and my mother. Now, of course, Einstein did earn his living at science, but for Einstein, science was not an occupation. It wasn't even a field of study. Science was life. Science was Einstein's pathway for realizing life's loftiest purpose, to discover the true nature of reality. Or as Einstein put it, to know God's thoughts, because everything else, he said, amounted merely to details. It was a mission that Albert Einstein would valiantly pursue until the very end. On April 17th, 1955, Albert Einstein experienced a painful tightening in his chest. He was admitted to Princeton Hospital where the doctors recommended surgery for what appeared to be a ruptured aortic artery. Einstein refused.
It is tasteless to prolong life artificially. I have done my share. It is time to go. I will do it elegantly.
As he lay in the hospital bed, Einstein reached for his notebook in the hope that he might yet complete his life's work, complete the leg of a journey he had been marching along for 30 years, complete what he called the unified theory, a theory that promised to stitch our understanding of all of nature's forces into a single mathematical tapestry. Even in those final hours, Einstein was driven by a supreme confidence that there was a unified theory, a master key that would unlock the secret code of the cosmos. It was a confidence radiating from a mind that had an uncanny, almost supernatural ability to meld with the natural world, a mind that nature herself had seduced some 70 years earlier. When Albert was 4, maybe 5 years old, he lay sick in bed, and to cheer up his young son, his father, Hermann Einstein, brought the boy a compass. And as young Albert Einstein twisted and turned and examined the compass and saw that the needle was mysteriously but reliably nudged northward, his hands grew cold. He trembled.
That this needle behaved in such a determined way did not at all fit with the nature of events, of effects connected with direct touch. I can still remember, or at least I believe I can remember, that this experience made a profound impression on me. Something deeply hidden had to be behind things.
The boy could feel the power of an unseen force, shaping and molding and controlling experience, filled him with awe, tinged with terror. Beneath perception, reality was guided by nature's hidden hand, and it was a hand that Albert Einstein would spend a lifetime yearning to grasp. Until he was 8 years old, Albert Einstein attended a German Catholic school, a fine tradition for good Jewish boys. He then transferred to the Leopold Gymnasium until he was 15, followed by a year of high school in Switzerland. Now, legend has it that Einstein was a poor student. After all, a version of that legend goes, one of Einstein's high school report cards shows his grade in mathematics plummeting from a 1, the highest in the fall, all the way down to a 6, the lowest in the spring. And we all love these stories, right? We soak them up, relieved to learn that even Albert Einstein began life ordinary. But there is always more to it. In this case, between those two terms, Einstein's high school, well, they changed their evaluation scale, making a 1 the lowest and a 6 the highest. You know, the old reverse the grading system trick to confuse future historians. Fact is, Einstein was the kind of kid who today would be nicknamed Einstein. By the time he was 15, he'd mastered differential and integral calculus. So if little Johnny fails math, he's not just like Einstein. But what is true, and emphatically so, is that Einstein had a deep disdain for authority, for rote learning, for any kind of institutional power.
Though the child of entirely irreligious Jewish parents, I came to a deep religiousness, which, however, abruptly ended at the age of 12. Through the reading of popular scientific books, I soon realized that much in the stories of the Bible could not be true. The consequence was a positively fanatic orgy of free thinking, coupled with the impression that youth is being intentionally deceived by the state through lies. It was a crushing impression. Mistrust of every kind of authority grew out of the experience. An attitude which never again left me.
It was an attitude that would fuel a fiercely independent engagement with the world. Einstein would learn on his own schedule. He'd study on his own timetable, and he would determine what was worthy of his attention.
The only thing that interferes with my learning is my education. I played the truant a great deal. At home, I studied the masters of theoretical physics with religious zeal.
Maxwell, Helmholtz, Boltzmann, Kirchhoff, Mach, Lorentz. These were Einstein's teachers. And when it came to studying for exams, well, Einstein would simply borrow the meticulous notes of his classmate, Marcel Grossman, and he'd generally scrape by. You see, Einstein had no desire for the usual accolades that motivated his fellow students, and he could not hide his contempt for rigid courses that covered the same old mandated material. Kind of makes me wonder what he'd think about the Common Core. Head of the physics department at the Zurich Polytechnic was Heinrich Weber. And during Einstein's first couple of years there, Weber gave a number of outstanding lecture courses and so had earned Einstein's admiration. But as Einstein's classmate Louis Kohlroas noted, that admiration quickly faded.
We waited in vain for a presentation of Maxwell's theory.
Referring to James Clerk Maxwell's new synthesis of electricity and magnetism, which Weber had apparently decided not to cover.
Einstein, above all, was disappointed.
And that disappointment, it ran deep. A few years earlier, when Einstein was 16, he had read popular accounts of Maxwell's theory that left him puzzled. Not because the books were unclear. Quite the contrary. Einstein had correctly learned that certain kinds of dancing electric and magnetic fields were in fact waves of light. But Einstein's fertile imagination took this realization one vital step further.
If I pursue a beam of light with the velocity of light, I should perceive such a light beam as at rest. However, such a thing does not seem to exist.
Now, granted, chasing after a beam of light is not the kind of thing that most of us would worry about. But even so, there is nothing particularly mysterious here in Einstein's reasoning. Much as a car on the highway appears stationary to somebody chasing it at the same speed, Einstein is saying that if you chase a beam of light at the speed of light, the light should appear stationary. You should be able to reach over and scoop up a handful of stationary light. But the thing is, none of you have ever held a handful of stationary light. And that's not like some weird coincidence shared by everyone who's come out for tonight's program. No one has ever held a handful of stationary light. And it was this seeming tension between the behavior of light and logical, intuitive understanding of motion that had been gnawing at Einstein. So he'd eagerly been awaiting Weber to present the math describing light. And when Weber decided that there were other, more important things to cover, Einstein scoffed, and from then on referred to his teacher as Herr Weber instead of the respectful Herr Professor Weber.
You're a very clever boy, Einstein, an extremely clever boy, but you have one great fault. You'll never let yourself be told anything.
Weber proceeded to reject one proposal after another which Einstein submitted for his final diploma requirement. And when the two finally did agree on a project and Einstein did the work, Weber rejected it because Einstein did not write the report on the correct sized paper. Hate it when that happens. You know, the romance of youthful rebellion, it was all well and good until Einstein realized that it was these very same professors that would determine his employment prospects. Einstein graduates in July 1900 with the less than stellar teaching diploma and sets about finding an academic job. He sends dozens of letters of inquiry, but rarely even receives a response. By 1901, Einstein is near despair. He needs a job. Marcel Grossman, that kid whose class notes helped Einstein to graduate, he once again proves to be Einstein's savior. Turns out that Grossman's father is friends with the director of the patent office in Bern, Switzerland. As Grossman tells Einstein, an opening is shortly expected. Indeed, in December 1901, Einstein gets the happy word that the patent office job at the rank of expert third class is his. It is now May 1905. Albert Einstein has been working at the patent office for nearly 4 years, and it is a busy and exciting time as the full potential of technology that harnesses electricity is beginning to emerge. And one fascination sweeping across Europe and reflected in the patent applications has to do with the synchronization of clocks. You see, in the old days, if a clock in Berlin and another in Bern were somewhat out of sync, no one much cared, right? Communication was just too slow for it to matter. But with the rise of the telegraph, distant locations are now becoming linked. So noon in Berlin and noon in Bern, they need to mean the same thing. And as railroads make the links yet more tangible, clock synchronization becomes yet more urgent as trains originating at distant locations, they need to adhere to the same track schedules. Scores of patent applications propose clock synchronization schemes, and it is up to Albert Einstein to determine if any of them have a shot of working. Now, within this immersion in clocks and synchronization, Einstein continues to ruminate on light and its speed, and it proves a potent mix. There's no way Einstein could have known it, but the solution to his decade-long puzzle about why we don't see stationary light, the solution to that puzzle is now just weeks away.
I spent almost a year in vain trying to modify the ideas of Lorentz in the hopes of resolving the problem. By chance, a friend of mine in Bern, Michele Besso, helped me out. It was a beautiful day when I visited with this problem. I started the conversation in the following way. Recently, I've been working on a difficult problem. Today, I come here to battle against the problem with you. We discussed every aspect of the problem. Then suddenly, I understood where the key to the problem lay.
Einstein left, and as he described it, a storm broke out in his mind. Light, electricity, magnetism, waves, frequency, motion, velocity, clocks, contraction, trains, transformation, simultaneity, synchronicity, space, time.
The next day I came back to Besso and I said to him, without even saying hello, "Thank you, I have completely solved the problem."
In the span of 5 frenzied weeks, the special theory of relativity is complete. And what Einstein finds is, by any conventional reasoning, utterly ludicrous. But a century of experiments have shown that Einstein was right and conventional reasoning dead wrong. The discovery hinged on an approach that future generations would label vintage Einstein. Look at something that everybody else has been staring at for decades, maybe even centuries, peel away all of the hidden assumptions, and see it differently. In this case, here's how this all played out. Everyone had long assumed that our intuition, our understanding of motion, remains valid even at speeds far greater than any we've ever directly experienced. Einstein challenged this. Sure, you can chase after a car, making its speed from your perspective appear to slow down or even appear motionless. But when the speeds are as enormous as the speed of light, Einstein said that this reasoning is completely wrong. Instead, he found that regardless of how quickly you chase after a beam of light, the light speed from your perspective will not slow down one iota. The light will continue to race away from you at exactly the same speed, because the speed of light never changes. The speed of light is constant. And that's why no one has ever caught up with a beam of light, and that's why no one has ever held a handful of stationary light. Puzzle solved. Or perhaps I really should say puzzle shifted, because the new puzzle is, how could light speed behave in such a crazy way? Well, think about speed for a moment. What is it? It's a measure of how far you go compared to how long it takes you to get there. So it's a measure of distance, space, divided by duration, time. So when Einstein said that the speed of light is constant, that the speed of light behaves weirdly, he was actually saying that space and time behave weirdly. And that's what set off the storm in his mind. He realized that space and time execute a fluid choreography in which they adjust themselves in tandem to keep the speed of light fixed. And that's what makes this all such a big deal. I mean, no one would really care that much about some esoteric, strange feature of the speed of light. But strange features of space, strange features of time, yeah, that matters. That speaks to strange features of reality. And Einstein was able to work out those strange features of reality, and he did it with nothing more than high school algebra. He found that if you have 2 clocks, one stationary and the other moving, that time will elapse slower on the moving clock compared to the stationary one. And it's not just that the clock's inner mechanism is running slow. Einstein found that time itself is slowing down, so all processes in motion slow, from aging to thinking to twerking. And completing the dance, Einstein also found that space behaves weirdly. If you have a couple taxi cabs, one stationary and another that rushes by at high speed, you'll find that the height and the depth of the speeding taxi cab unchanged, but its length in the direction of motion will be shrunken. And were I to jump into that squeezed taxicab, you'd think I'd crave some legroom, but actually, relative to my new perspective, it's the rest of the world that's rushing by me, so the interior of the taxi appears ordinary. And it's the outside world that undergoes all these wondrous distortions. At everyday speeds, these effects are too small for us to notice. But if we routinely traveled near the speed of light, that's fast enough to go around the entire Earth 7 times in a single second. At those speeds, these effects, they would be obvious. We'd experience them all the time. But because we generally do not travel near the speed of light, it took the genius of Einstein to leap beyond everyday experience and figure this all out. Einstein completes his paper on special relativity in late June of 1905. And the presentation itself was peculiar. The paper did not have a single reference, and it began by addressing issues that the world's leading physicists would likely have considered in little need of exposition.
If I say that train arrives here at 7 o'clock, I mean the pointing of the small hand of my watch to 7 and the arrival of the train are simultaneous events.
A young upstart who'd yet to receive his doctorate instructing the world's leading thinkers on the meaning of the little hand. But those who read Einstein's paper, they quickly realized that his singular focus on concepts that everybody else had taken for granted had changed our understanding of space and time.
This relativity principle has brought about a revolution in our physical picture of the world, which in its extent and depth can only be compared to that produced by the Copernican world system.
Henceforth, space by itself and time by itself are doomed to fade into mere shadows, and only a kind of union of the two will preserve an independent reality. It came as a tremendous surprise. I really wouldn't have thought Einstein capable of that. For in his student days, Einstein had been a lazy dog.
With such a radical assault on established science, it is remarkable how quickly Einstein's ideas were accepted. In just a few years, German and British American physicists, they embraced the special theory of relativity. But even so, and especially as Einstein gained ever greater prominence, there were those who held to a different perspective.
It is part of Jewish physics, for the Jew wants to create contradictions everywhere and to separate relations so that preferably the poor, naive German can no longer make any sense of it whatsoever. Einstein's work never was intended to be true. The Jew conspicuously lacks any understanding of the truth beyond a merely superficial agreement with reality.
Einstein took all reactions, good, bad, ugly. He took them all in stride because he was saving his energy for the only truly worthy opponent, the universe. And here in 1905, he had already scored a great victory, a triumph in round 1. But that would prove merely to be a warm-up for the epic battle looming on the horizon. Round 2. You know, what happens in science, sometimes you resolve one problem only to open up a whole nother can of worms. And that is what happens with the discovery of special relativity. It surely does resolve the puzzle of light speed, of why we never see stationary light. But in the process, it reveals another puzzle to do with a different speed, the speed of gravity. In the late 1600s, Isaac Newton wrote down his famous universal law of gravity, which says that every object in the universe pulls on every other with a force that depends on 2 things: how big the objects are, their mass, and how far apart they are in space. And using the little mathematical version of that description, we can make predictions for the motion of moons, planets, comets, and it all works, which is great. The problem has to do with the speed with which gravity exerts its influence. Here's what I mean. Imagine that for some reason, and the details do not matter, the sun is plucked out of space. It's gone. Here's a question. How long will it take for us to learn that the sun has disappeared by the sky going dark? Well, how long does it take light to travel from the sun to the earth? About 8 minutes. Which means if the sun were to disappear right now, the earlier light it emitted will still be streaming toward the earth, still be streaming toward the earth, still streaming, and only 8 minutes later will the final light that the sun emitted blow by planet Earth, and the sky goes dark. By comparison, how long will it take for us to learn that the sun has disappeared by feeling it? And I don't mean like feel it emotionally. I mean feel it physically. The sun keeps the earth in orbit, so if the sun disappears, our motion through space will change. But how long will it take for us to feel that change in our motion? Well, according to the equations of Isaac Newton, at the very moment that the sun disappears, its gravitational pull will also disappear, so we will be flung out of orbit immediately. Which means we will learn that the sun has disappeared by a change in gravity 8 minutes before we learn that it's disappeared through a change in light. Gravity going faster than light. That flew in the face of special relativity's dictum that nothing can go faster than the speed of light. What to do? Well, Einstein realizes he needs to resolve this problem with the speed of gravity. And to do that, he realizes he needs to get a handle on how gravity works. You see, the formula that Isaac Newton gave us describes the influence of gravity, but it does not tell us how gravity exerts that influence. I mean, how does the sun keep the earth in orbit? You say it's gravity, but there's no rope, no tether, no arm that reaches out. So by what mechanism does gravity exert its influence across the vacuum of empty space? This was a question that deeply troubled even Isaac Newton himself.
It is inconceivable that inanimate brute matter should, without the mediation of something else, affect other matter without mutual contact. That gravity should be innate, so that one body may act upon another at a distance through a vacuum, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it.
And yet, even though Newton aspired to go beyond that absurdity, he was never able to answer the question of how gravity works.
I leave that question to the consideration of the reader.
Yeah, sure. For the following 200 years, just about everybody who read that, they kept on reading. Here's where Einstein is different. He is motivated to figure out how gravity works, and one afternoon in the patent office, Einstein sees the way forward.
In 1907, I was preparing a summary of the results of the special theory of relativity for the Jahrbuch der Radioaktivität at the request of Stark, the editor of the journal. I was sitting in a chair in the patent office at Bern. Suddenly, an idea dawned on me. If a man falls from the roof of a house, he must not feel his weight himself. I was startled. It was the happiest thought of my life.
The happiest thought of Albert Einstein's entire life is a man falling from the roof of a house. But the reason this thought made Einstein so happy is that within it, he could see the key to a generalized version of relativity that would embrace the force of gravity. Here's how I can think about it. Imagine that I am the guy who in just a moment Einstein will see falling from that roof. But just before that, I'm on the roof, standing on my bathroom scale. I look down at the scale and it reads 160 pounds. Then, with the scale Velcroed to my shoes, I jump. And as I'm falling, I again look down at the scale. What will it read now? Well, because the scale is falling right with me, I'm unable to press down upon it, so the reading on the scale will drop all the way to 0. By going into free fall, I feel weightless. And it's not just the scale. If I were to empty my pockets everything will also fall right with me. So as I look over, it'll all be hovering right next to me, exactly as it would if there were no gravity. So in this sense, from my perspective, I have canceled gravity out. What about from your perspective? Watching this from the ground, well, you will surely say that there is gravity, right? It's what's pulling on me, causing me to fall faster and faster, causing me to accelerate downward. It's not as though one perspective is right and the other is wrong. Both perspectives are right, yours and mine. And therein lies the power. By putting the two perspectives together, Einstein realized that there is a profound connection between acceleration and gravity. You see accelerated motion, my falling faster and faster, and I see gravity being canceled. And this is one of the rare insights of Albert Einstein that you can verify at home, safely. All you need is a bottle of water. Water is spraying out of those holes because gravity is pulling on the water. But if we let the bottle drop, then from the water's perspective, gravity will be canceled, and so it should stop spraying out. And it does. Accelerated motion canceling out gravity. Now, the reverse is also true. Accelerated motion can masquerade as gravity. It can mock up a force that's indistinguishable from the pull of gravity. That room, it's in completely empty space, no gravity. And yet, if we turn on a couple of rocket boosters, making the room accelerate upward, everything inside feels pulled downward by a force that feels just like the pull of gravity. That feel like gravity?
Big time.
So the upshot is that with his happiest thought, Einstein realizes that he can seamlessly trade off accelerated motion and gravity. And this proves to be the vital leap forward, because understanding gravity, that was surely difficult. It had stumped Isaac Newton and everybody else who thought about it for 200 years. But understanding accelerated motion, that didn't seem so bad. So Einstein sees accelerated motion as his newfound hammer for cracking the problem of gravity, figuring out how gravity works. And it would not take long for this strategy to bear fruit, to reveal a connection between gravity and another startling concept, the curvature of space and time. When Albert Einstein has a new idea, a good idea, he does not let it go. He shakes it, he twists it, he caresses it in search of a jewel that may be hidden inside. And that's what happens with this newfound link between accelerated motion and gravity. Einstein's mind returns again and again to images of people falling from roofs, rooms accelerating in empty space, or falling down toward the earth. And in the process, he realizes something profound. Imagine that I am in one of those rooms, freely falling toward the earth. And as I'm floating around inside, I click on a laser. What will I see? Well, this is not a trick question. I'll see the laser light go straight across the room and hit a corresponding point on the opposite wall, that red dot over there. But what will you all see watching this from the surface of the earth? Well, you will surely agree that the light begins at the laser and ends at that red dot. But because from your perspective, gravity is causing the room to accelerate downward, you will see the light go in a curved trajectory. After all, that is the only way that the light can begin at the laser and end at the red dot, given that from your perspective, the room is falling ever more quickly while the light is in transit. What's the conclusion? In a gravitational field, light falls. As light sweeps along the contours of space imbued with gravity, it traces out curved trajectories, a direct link between gravity and curvature. And with this vital insight, Einstein can begin to see the glimmers of a new understanding of gravity taking shape. The idea is that if there's no matter, no gravity, then space is not curved. But if we bring in a massive body like the sun, then the environment, it responds. The environment warps. the environment curves in response to the presence of the sun, in response to the motion of the sun. And if we were to take a two-dimensional slice through this environment, we see that the Earth itself is kept in orbit because it's rolling along a valley in a curved environment that the sun creates. This is Einstein's proposal for how gravity works. Warps and curves in the fabric of space and time. And it's not a proposal that's meant to only work out there in outer space. It's meant to work everywhere, even here. As a body moves along, the environment, even here, it responds. It ripples. It curves in response to the motion of that body, in response to the presence of that body. And it's an idea that also applies to me, right? Now look, I am not a particularly big dude. So the curvature I'm creating is too tiny for you to feel. But according to Einstein, it is here to be sure, as this is the essence of Einstein's proposal. And what a beautiful proposal it is. You and I, the Earth, the Moon, the Sun, we are all surfing along the warps and curves in space and time, sliding along its chutes and valleys. Yet, however striking the idea, Einstein realized that there is still a monumental challenge ahead. He needs to marry mathematical might to this spectacular imagery. He needed to come up with equations that will predict the precise shape and amount of curvature in response to any given amount of matter or energy in space. But even so, even with the daunting challenges ahead, for the very first time in his life, Albert Einstein can feel that he is touching the fingertips of nature's hidden hand. Between 1908 and 1911, Einstein writes a couple dozen papers in physics, but none of them on gravity. Instead, he is focused on the early developments of quantum theory, while also wandering the academic world, from an initial post in Zurich to a follow-on post in Prague, and finally in 1912 back to Zurich. Now, during all this meandering, Einstein continues thinking about gravity, but it's his move back to Zurich that marks the turning of his full attention to the problem of gravity, figuring out how gravity works. And more established scientists who've been kind of keeping tabs on Einstein's preoccupations, they considered this focus on gravity to be foolhardy.
As an older friend, I must advise you against it. For in the first place, you will not succeed. And even if you do succeed, no one will believe you.
Einstein, surprised, ignores all the advice, and his famed Zurich notebook allows us to peer directly over his shoulder as he launches a full-throttled attack on gravity. First few pages of the notebook, Einstein is just summarizing known physics in the new language of space and time brought forward by special relativity, and nothing new here, just old ideas in a new formalism. But then we come to page 14. And like a bolt from the blue, Einstein begins this page with a simple, modest-looking formula that heralds one of the most dramatic of all scientific upheavals. The formula, it's a generalization of the Pythagorean theorem that we all learned in junior high school. Remember how that goes? You have a nice triangle like this, then a squared plus b squared equals c squared. Thank you. But if this triangle is warped, if it's curved, you can imagine that a squared plus b squared will no longer equal c squared. Instead, when it's curved, you need a new formula. And that's what the formula on the top of page 14 provides. Einstein's own little doodling in the margins lets us see what pushed him in this direction. Grossman, Marcel Grossman, yeah, the very same kid whose class notes helped Einstein to graduate. The same kid whose father finagled a job for Einstein at the patent office. That kid, is now a professor of mathematics at the Zurich Polytechnic. So when Einstein returns to Zurich, he decides to drop in on his old friend for a little casual advice on how to describe curvature mathematically.
Grossman, you must help me, or I shall go crazy.
Grossman obliged.
I looked over the literature and soon discovered that the mathematical problem was already solved. The entire development followed the Gaussian theory of curved surfaces, which was the first systematical use of generalized coordinates. Riemann's achievement was the biggest. He showed how one can form a field of tensors, GIK, of the second differentiation rank.
Marcel Grossman, ladies and gentlemen. But yes, that mathematical gibberish really does mean something, something important. Grossman had found that the math for describing curvature had already been worked out in the 1800s, which would mean Einstein would not have to start from scratch. But the papers themselves, they gave Grossman pause. The equations were dense and cumbersome.
It is a terrible mess. Physicists should not be involved with it.
Which only encourages Einstein to dive right in. And he quickly concludes that the situation is actually stunningly fortuitous. Sitting on the dusty shelves of the library is the mathematical architecture that might very well allow him to construct his generalized version of relativity. To top it off, Einstein would not have to go it alone. He had his old friend Marcel Grossman to guide him through the mathematical thicket.
I'm now occupied exclusively with the gravitational problem and believe I can overcome all difficulties with the help of a local mathematician friend. But one thing is certain. Never before in my life have I tormented myself anything like this. And that I have gained great respect for mathematics, whose more subtle parts I'd considered in my ignorance until now as pure luxury. Compared with this problem, the special theory of relativity is mere child's play. Whew.
In the Zurich notebook, we see Einstein immersing himself in that mathematics. He's trying out the notation over here. He's doing rudimentary calculations over there. Now, today, all this material is standard. I teach this to undergrads. But in 1912, all of this material was foreign. But even so, Einstein quickly gets the hang of it, allowing him to push forward on two parallel tracks. First, Einstein uses the mathematics to guide him toward equations that will be general, in the sense that they will work equally well whether you're sitting still or falling from a roof. Remember, that is the general of general relativity, and Einstein's happiest thought convinces him that it is essential. Second, Einstein uses physical reasoning to make sure that any new equations make sense. Most importantly, they have got to reduce to the equations of Isaac Newton in ordinary situations like tossing a rock or the motion of the moon. Situations in which Newton's ideas had already received a couple hundred years of observational support. And as we turn the pages of the notebook, we see that these two tracks are converging. Einstein is hot on the trail of the general theory of relativity. And I gotta tell you, when I read these pages as a physicist, even though I kind of know how it all turns out, I can't help but cheer Einstein on. I mean, go, Einstein, you're almost there. And then with the prize just coming into his grasp, he stumbles in trying to extract Newton's gravitational equations from his own. Einstein makes a technical assumption. It's over here, page 42. Now, of course, you don't have to know what this symbol means, but this represents an assumption about the shape of the environment outside a spherical body like the Earth. And it's wrong. And with that mistake, Einstein cannot get the mathematics to work out. So what to do? Well, Einstein, he regroups, he fights back. He comes up with all sorts of mathematical modifications, clever manipulations, but in the end, nothing will work. Einstein throws up his hands. Moment of utter despair. He thinks that perhaps for all these years he's been barking up the wrong tree. Now, others in this situation would plain give up, but not Einstein. He keeps focused. He gets together with Marcel Grossman, and the two of them come up with a new strategy for describing gravity, a strategy, and this is important, in which Einstein retreats from his happiest thoughts. He gives up on finding equations that will work equally well for you, me, someone who's wildly moving. In 1913, the two of them published this idea. And it's this paper right here that marks the opening stride of 2 long years of wandering in the dark. Because only after Einstein had seen this approach through and realized that it did not work would he finally be ready to get back on track toward the general theory of relativity. But by then, the playing field would no longer be just his. Einstein's big job offer comes in July of 1913. Max Planck and Walter Nernst, these were giants of German science. They visit Einstein and make him an offer he cannot refuse. Move to Berlin, head up a new Institute of Physics, and become the youngest person ever to be inducted into the Prussian Academy of Sciences. In the spring of 1914, Einstein makes the move, and in Berlin, he continues to develop the idea that he and Grossman had published. He begins to see possible fractures in the foundation of this new approach, but by June of 1915, he is still sufficiently confident to accept an invitation from the University of Göttingen to give a week-long series of lectures on his ideas. And in the audience for those lectures is the renowned mathematician David Hilbert. And Einstein's discussions with Hilbert, well, they please him no end.
I was able to convince Hilbert of the general theory of relativity. He is a man of astonishing energy and independence. I am quite enchanted with Hilbert.
Early 20th century bromance. But then things take a sharp turn. In October of 1915, Einstein realizes that he made a mistake in an earlier and pivotal calculation that completely and totally undermines his confidence in the approach that he and Grossman had published. 2 long, fruitless years. It finally convinces Einstein that he should not and he could not abandon his happiest thought, that it is absolutely imperative that any new accommodations of all perspectives, whether sitting still or freely falling or wildly moving, and so Einstein returns to the ideas that he had been developing toward the end of the Zurich notebook. Now, far greater facility with the mathematical methods. And as Einstein combines and recombines the metric and curvature tensors handed down to him by the deans of 19th century geometry, he reports on his progress in a series of lectures at the Prussian Academy. It's now Thursday, November 4, 1915.
For the last 4 years, I have tried to establish a general theory of relativity on the assumption of the relativity of even non-uniform motion. Yeah, I actually believe that I discovered the only law of gravitation which was in line with a logically conceived general postulate of relativity.
Einstein then describes the problems that beset his approach with Grossman and the impact it had on his perspective.
For that reason, I completely lost trust in the field equations, and thus I went back to the requirement of a more general covariance.
That's the technical term for equations that work regardless of how you are moving.
Which I'd abandoned only with a heavy heart. Back then we had, in fact, already come quite close to the solution.
Einstein concludes the lecture with equations that are tantalizingly close to fitting the bill, but he's not quite there and he knows it. And he pursues the math with the intensity of a lion stalking its prey. He writes to his son that he's so engrossed in his calculations that he sometimes forgets to eat. Now, in the midst of this intense intellectual focus, word trickles down to Einstein that David Hilbert has also found the flaws in Einstein's paper with Grossman and is throwing his hat into the ring seeking the correct resolution. Out of left field, Einstein realizes that there's a chance he might get scooped. Bromance on the rocks. Einstein immediately writes to Hilbert and lets him know that he'd already found those flaws and backs up the claim by sending Hilbert a copy of the presentation that he'd given a few days earlier at the Prussian Academy.
With return post, I am sending you the correction to a paper in which I changed the gravitation equations after having myself noticed about 4 weeks ago that my method of proof was a fallacious one. My colleague Sommerfeld tells me you also have found a hair in my soup that has spoiled it entirely for you. I'm curious whether you will take kindly to this new solution.
It is now Thursday, November 11, 1915. Einstein is again lecturing at the Prussian Academy, unleashing the full geometrical arsenal now under his command. But the pieces have yet to fully coalesce, and increasingly concerned about claiming the generalized theory as his own, Einstein sends a copy of that presentation to Hilbert. Hilbert's response knocks Einstein back on his heels.
I have a solution to your great problem. I had first wanted to think through the physical implications further, but since you are so interested, I would like to lay out my theory in very great detail this coming Tuesday. That is, the day after tomorrow. You can arrive at 3 or 5:30. My wife and I would be very pleased if you would stay with us. P.S. As far as I understand your new paper, the solutions given by you are entirely different from mine.
Einstein is freaked. He'd been working toward the generalized theory for nearly a decade. He had freely shared all of his thinking that June with Hilbert, and now Hilbert, racing him to the finish line, claims he's figured it all out. The very last thing that Einstein wants to do is go and meet with Hilbert and be lectured on a solution that he himself has almost completed, and possibly have to concede that Hilbert got there first.
Your analysis interests me tremendously. The hints you gave in your postcards awaken the greatest of expectations. Nevertheless, I must refrain from traveling to Göttingen for the moment, and rather must wait patiently until I can study your system from the printed article. For I am tired out and plagued by stomach pains besides.
During the following days, Einstein redoubles his effort, but with a shift in focus. He decides to target a long-standing problem in Newtonian gravity, having to do with the motion of the planet Mercury, realizing that if his new approach could shed light on this problem, it would be enormously convincing. The problem is that Mercury's orbit doesn't quite close on itself the way Newtonian gravity says that it should. Instead, the orbit shifts by a little bit each year, by about 1/10,000th of a degree. That comes to about 43 arc seconds over the course of a century. Now, astronomers had come up with all sorts of strained explanations for this, like the possibility of an undetected planet tugging on Mercury, but none of it was convincing. So Einstein decides to apply the equations he's been developing to Mercury's orbit. And when he finishes the calculation, Einstein stares at the page. The astonishment was not unlike what he felt as a young boy with a compass, because the calculations revealed that Mercury's orbit should shift by 43 arc seconds per century. Abraham Pais, Einstein's friend and biographer, described this as the most powerful emotional moment in Einstein's scientific life, perhaps in all of Einstein's life. Einstein himself confides in his friend Adrian Fokker that when the calculations agreed with the observations of Mercury, Einstein said he got palpitations of the heart. But Einstein told his colleague von der Haas is perhaps even more revealing. Einstein said that when his calculations explained the observations, he said that he could feel something snap inside him. Nature had spoken to him. It's now Thursday, November 18, 1915. Einstein is all set to lecture on these wondrous results on Mercury's orbit when that morning his triumphant mood shatters. He receives a paper from David Hilbert.
But the system you furnish agrees, as far as I can see, exactly with what I found the last few weeks and presented to the Academy. The difficulty was not in finding generally covariant equations, for this is easily achieved with Riemann's tensor.
referring to equations that he had developed years earlier in the Zurich notebook.
We had distanced ourselves from those equations reluctantly because it seemed to me there was an incongruity with Newton's law. The important thing is, these difficulties have now been overcome. Today, I am presenting to the Academy a paper in which I derive quantitatively out of general relativity without any guiding hypothesis the perihelion motion of Mercury. No gravitational theory has achieved this until now.
Cordial congratulations on conquering the perihelion motion. If I could calculate as rapidly as you, in my equations, the electron would have to capitulate and the hydrogen atom would have to produce its note of apology as to why it does not radiate. Please keep me up to date on your latest advances.
The conciliatory response may have momentarily eased Einstein's growing anxiety, but what he did not yet know is that on the very next day, Saturday, November 20th, Hilbert submits his paper for publication, apparently laying claim to his version of the general theory of relativity. The title of Hilbert's paper was appropriately subdued. Unaware of this, but feeling the mounting pressure, Einstein gives his lecture on Mercury's orbit and then turns to sprint for the goal that he's been chasing for nearly a decade. But from almost every corner of his life, Einstein is under assault.
Papa. Wo bist du, Papa? Albert. Wo bist du, Vater?
Wir brauchen Geld.
Albert!
Wo bist du, Vater?
Albert.
Gegenwart.
Papa.
Vater.
Albert!
Werden Sie meine Arbeit lesen?
Annie, komm in. Albert! Ich vermisse dich.
Papa. Albert.
Wo bist du, Albert?
Albert!
Albert.
Somehow, amidst the chaos, Einstein undertakes a final flurry of geometrical gymnastics and coaxes the field equations to fall fully and firmly into place. It is now Thursday, November 25, 1915. Einstein is lecturing at the Prussian Academy for the fourth time in as many weeks.
With this, we have finally completed the general theory of relativity.
Einstein has the equations. The left-hand side is geometry. It describes warps and curves in the fabric of space and time. The right-hand side keeps track of the matter and energy within and moving through a region of space and time. And the equality, what we now call the Einstein field equations, this provides the choreography for the entwined cosmic dance of space and time, matter and energy. And remarkably, the equations tell a story that's a little different from the imagery I've been using. The imagery used in just about every popular account, which focuses upon the curvature of space. Because the math shows that time curves too. Time warps, which means that clocks that are ever deeper in a gravitational field, they tick off time ever more slowly. In fact, in ordinary situations like tossing a cup, it is the warping of time that has the greatest impact on the resulting motion. And yet, for a body like the Earth, the size of that time warp, it's tiny. I mean, your heads are all generally a little higher up in Earth's gravitational field compared to your feet, which means your heads age a little more quickly than your feet, over the course of an average lifetime by about 100 billionths of a second. And yet, according to general relativity, that tiny time warp, that's why things fall. That's why you're anchored to your seats. Objects do not want to age. The math shows that things are drawn toward locations where time elapses more slowly. Who would have thought that the seemingly basic question asked by Isaac Newton 240 years earlier, how does gravity work, would result in such a dramatic upheaval in our understanding of reality?
I am quite overworked from the extraordinary exertions of the last few months, but the success is glorious.
One can barely imagine the elation of that glorious success. But Einstein is also now deeply concerned. He learns that Hilbert submitted his paper 5 days before him. And indeed, in the decades since, the priority for the discovery of general relativity has been debated. I mean, in that final chaotic week, did Einstein come up with the final form of the equations on his own, or did a little glance at Hilbert's paper show him the way? Did Hilbert's paper actually have the final form of the equations, or did Hilbert modify his paper prior to publication based on Einstein's insights? Part of the resolution has been lost to history, as a key section of the page proofs of Hilbert's paper have been snipped away, literally snipped away, by design, by chance, no one knows. But in the published version of his paper, Hilbert did not challenge Einstein for the discovery of the general theory of relativity.
The differential equations of gravitation that result are, as it seems to me, in agreement with the magnificent theory of general relativity established by Einstein.
There has been a certain ill feeling between us, the cause of which I do not wish to analyze. I have struggled against the feeling of bitterness attached to it with complete success. I think of you again with an unmixed geniality and ask you to try to do the same with me. It is a shame when two real fellows who have extricated themselves somewhat from this shabby world do not afford each other personal pleasure.
The road to the general theory of relativity was long. It was windy, bumpy, anxiety-provoking. The final result, a jewel. The theory was now done, but Einstein realized that there was still one remaining question. Is the general theory of relativity right? His use of the equations to explain Mercury's orbit was impressive, but a truly convincing test would require the theory to make a prediction about something not yet observed that scientists could go out and measure. Einstein knew just what to do. Since his earliest work toward the general theory of relativity, Einstein knew that in a gravitational field, light falls. Light travels along curved trajectories. And now, with the final form of the equations in hand, he could calculate the precise shape of those curved trajectories. So Einstein proposes testing those predictions through astronomical observations. Here's how. Light from a distant star travels along a nice straight trajectory when the Earth is on this side of the sun. But 6 months later, when the Earth is on the other side, that starlight needs to go through the warped region near the sun, which from Earth makes the position of the star in the sky appear to shift. Using the math of general relativity, Einstein was able to calculate the angle between those two locations, and it comes out to be 1.75 arc seconds. That's roughly the same as the angle between the bottom and the top edge of a dime viewed from 2 miles away. Tiny, but measurable. But doing so would require seeing distant stars during the day while the sun is out. I mean, how do you do that? Well, during a solar eclipse, the moon blocks out the sun's light, making the distant stars visible. So to test Einstein's prediction, astronomers would need to take photographic plates during a solar eclipse and compare them with photographs taken 6 months earlier. The British Astronomer Royal, Sir Frank Dyson, immediately set plans in motion to test this prediction during the upcoming solar eclipse of May 29, 1919. And Dyson taps fellow British astronomer Arthur Eddington to help organize the observational teams. Now, Eddington was himself an early and public champion of the general theory of relativity. In fact, during one of his own public lectures on the subject, an audience member commented,
Professor Eddington, you must be one of the 3 people in the world who understands Einstein's theory.
When Eddington didn't answer, the audience member encouraged him.
No need to be modest, Eddington.
On the contrary, I'm trying to think who the third person is.
Eddington and Dyson organized 2 teams to head out to locations that will experience a total solar eclipse. The city of Sobral near the Amazon jungle and Principe off the west coast of Africa. The challenge was weather. On the morning of the eclipse in Principe 100 years ago today, the rains were torrential. And as the 2:13 p.m. eclipse approached, the sun toyed with the astronomers, poking through the clouds, winking away, reappearing. Finally, with just a couple minutes to go, the cloud cover cleared, and the astronomers took as many photographic plates as they could. The weather in Solbral was somewhat better, but that team suffered from its own challenges, largely to do with technical issues with the equipment, so their data was also far from pristine. So the final result would require a careful blending of all the observations, analysis that would take a couple of months. Einstein waited patiently for the results.
If my theory of relativity is proven successful, Germany will claim me as a German. The Swiss will call me Swiss, and France will declare that I am a citizen of the world. Should my theory prove untrue, France will say I'm Swiss, the Swiss will say I am German, and Germany will declare I am a Jew.
Finally, on September 22nd, 1919, Einstein receives a telegram summarizing the results of the expeditions, and he does what any good Jewish son would.
Dear Mother, today a joyful notice. H.A. Lawrence has telegraphed me that the English expeditions have really proven the deflection of light at the sun.
It was astonishing. Einstein's wild ideas about warps and curves in space and time, it wasn't pie in the sky. It was real. Einstein had used complex math to fashion a new understanding of gravity, and the universe somehow knows about the math and obeys the equations. During all the well-deserved congratulations, a student asked Einstein what he would have said had the observations not confirmed his prediction.
I would be sorry for our dear Lord, for the theory is correct.
The official public announcement took place in November 1919 at a meeting of the Royal Society in London.
The results of the expeditions to Sobral and Principe leave little doubt that a deflection of light takes place in the neighborhood of the sun, and that it is of the amount demanded by Einstein's generalized theory of relativity.
The Times of London, the New York Times, just about every other newspaper in the world picked up the story, and with the media frenzy, there was an intense public interest to learn about relativity, which catapulted Einstein virtually overnight into a revered figure worldwide. It was an enormous triumph for science, for human ingenuity, for Einstein. Einstein, the public figure, he knew this well. But for Einstein, the scientist, this was merely a step, albeit an important one, toward the ultimate goal. The unified theory. Einstein was the toast of the town. Every town, everywhere, his wild hair and his impish smile, it all just propelled him ever higher in the public eye. He was a character, in the truest sense of the word, a buoyant persona ready-made for public admiration. There was a widespread sense that to experience Albert Einstein was to brush up against the heights of humankind's defining qualities. Sometimes, even just the opportunity to learn about Einstein and his work could drive the public to excess. On January 5th, 1930, a film about Einstein and relativity was scheduled to be shown at the American Museum of Natural History in New York City. A reporter for the Chicago Tribune described the scene.
A mob of 4,500 persons gathered to hear about the Einstein theory suddenly charged the attendants guarding the door. Shouting exultantly, the rioters swarmed between the canoes, totem poles, and walrus tusk ornaments to the main auditorium and seized the remaining seats. The less agile were knocked down and stepped on. Women screamed. Frantic knowledge hunters begged to be admitted. Bruised and tearful women pleaded with the overflow mob. Finally, the police quelled the first science riot in history.
Certainly, the reverence Einstein commanded also manifested in more refined ways.
When I was a very young man, just beginning to make my way, I had been invited to dine at the home of a distinguished New York philanthropist. After dinner, our hostess led us to an enormous drawing room. Other guests were pouring in, and my eyes beheld two unnerving sights. Small gilt chairs were being arranged in long, neat rows, and up front, leaning against the wall, were musical instruments. Now, I am almost completely tone deaf. So, as the after-dinner music began, I fixed my face in what I hoped would read as an expression of intelligent appreciation. At once, I heard a quiet but surprisingly penetrating voice on my right.
You are fond of Bach?
I was sitting next to Albert Einstein. Now, I knew as much about Bach as I did about nuclear fission. Awkwardly, I replied, I've never heard any of his music. A look of perplexed astonishment washed over Einstein's face as if I'd said I'd never taken a bath. He took me by the arm and led me out through the crowded room as a rising murmur of puzzled speculation followed us out into the hall. Resolutely, he led me up the stairs.
Now, tell me, please, is there any music you do like?
Well, I like songs that have words. Einstein quickly went to a corner of the room. He opened a phonograph and started pulling out records. He turned on the record, and at once the study was filled with the sounds of Bing Crosby's Where the Blue of the Night Meets the Gold of the Day. Einstein beamed at me and kept time with the stem of his pipe. After 3 or 4 phrases, he stopped the phonograph.
Now, tell me what you have just heard.
The simplest answer seemed to be to sing the lines. I did just that, trying desperately to stay on tune. When the blue of the night meets the gold of the day. The expression on Einstein's face was like the sunrise.
There, you see, you do have an ear.
Einstein found another record and set it going. The golden voice of John McCormick singing The Trumpeter filled the room. After 3 or 4 lines, Einstein stopped the record and asked me to sing it back. I did, then Caruso, and this was followed by about a dozen more. I could not shake my feeling of awe over the way this great man, into whose company I'd been thrown by chance, was completely preoccupied by what we were doing, as though I were his sole concern. We came at last to recordings of music without words, which I was instructed to reproduce by humming. As I reached for a particularly high note, Einstein opened his mouth wide and threw his head back as if to help me attain what seemed unattainable. Ah! Evidently, I came close enough, for Einstein suddenly stopped the phonograph.
Now, young man, we are ready for Bach. Just allow yourself to listen. That is all.
It was a glorious time. Einstein had heard the harmonies of nature, and with his precious generalized theory, had shared the music that was resonating in his mind with the world. And the world stood at the ready for Einstein's next move, which he promised would be the coveted unified theory. A theory that would embrace not just gravity, but all of nature's forces in a single coherent mathematical formalism. It would be the master equation underlying physical reality. Einstein finished his first paper on unification during a long boat trip to Egypt in 1923. And with his newly minted rock star status, that paper created quite a stir. In just a few years, Einstein realized that that paper was flawed, but by then he was already developing a new idea called distant parallelism. And journalists far and wide caught wind that that paper would be released toward the end of January 1929, and did they ever stoke the public's Einstein mania with breathless articles. And when the paper finally did appear, the London department store Selfridges pasted its pages in its storefront window, attracting these massive crowds, all straining to catch a glimpse of Einstein's latest breakthrough. And in New York, the Herald Tribune, calling Einstein a near mystic, publishes his paper in its entirety on the front page.
Now, but only now, we know that the force which moves electrons in their ellipses around the atom is the same force which moves our Earth in its annual course around the sun, and the same force which brings us the rays of light and heat, which makes life possible on this planet.
Wow. Thrilling. But in less than a year, Einstein realizes that that approach is flawed. By then, he's already developing other ideas widely covered, with the pattern repeating again and again.
Einstein's never-failing inventiveness, as well as his tenacious energy in the pursuit of his target, blesses us with about one such theory per year, in which it is psychologically interesting that the current theory is usually regarded by its author for a while to be the definitive solution. I propose we greet each new theory with Einstein's new field theory is dead. Long live Einstein's new field theory.
In 1933, Einstein makes the final academic move of his life. With the Nazis on the rise in Germany, Einstein accepts a position at the Institute for Advanced Study in Princeton, New Jersey. And ensconced in America, he continues his quest toward the unified theory, while also waging a relentless attack on quantum theory. 1935, Einstein writes one of his final papers of lasting significance on a curious feature of quantum mechanics in which supposedly two distant particles can influence each other instantaneously. Einstein called it spooky. Spooky action at a distance. He thought it was nonsense, bolstering his view that quantum theory could not be the final word, as its proponents had claimed, strengthening his conviction that the missing piece was a unified theory he was developing. Now, Einstein could have been right, but experiments, many done long after he died, showed that spooky action is real. Einstein had held to a reasonable, a sensible perspective, but it was as if his intuition was just no longer in sync with the rhythms of the universe. And as with his intuition, so with the rhythms of the world, as the rumblings of war began to reverberate across the Atlantic. 1939, Einstein is vacationing at Peconic Bay, Long Island, when he unexpectedly receives a visit from two colleagues who show him that recent results in atomic physics might be co-opted to build a weapon of ferocious energy. Fearful that German scientists might get there first, Einstein urges President Roosevelt to act. Roosevelt does. On August 6, 1945, Einstein wakes up from his afternoon nap, and his assistant informs him that an atomic bomb has been dropped on Hiroshima.
Oh my God. The unleashed power of the atom has changed everything. Save our mode of thinking. We drift toward unparalleled catastrophe. I know not with what weapons World War III will be fought, but World War IV will be fought with sticks and stones.
Even though Einstein had nothing to do with the Manhattan Project, because of that letter to Roosevelt, and also because his famous equation, E equals mc squared, can be used to calculate energetic yields, some called Einstein the father of the atomic bomb. It was a devastating public perception that Einstein could never shake. And so as the years continue to pass, Einstein grows ever more isolated from mainstream physics, retreating into the comforting world of ideas that he has inhabited for nearly a lifetime.
In many elusive moments, I appear to myself like an ostrich with his head forever buried in the relativistic sand in order to avoid the evil quanta. One builds creates a small world, and one feels miraculously great and important, just like a mole in its self-dug hole.
Einstein stays the course, making use of the mathematical methods that had proved so potent in its discovery of general relativity, methods which, as everybody else could see, were unable to bring the unified theory any closer.
Einstein, in his later years, got rather detached from the work of physics in general, and he stopped reading people's papers. He kept working on the same problem he had started working on as a much younger man. It is as if a general who is a master of horse cavalry, who's achieved great things at the beginning of the First World War, would later try to bring that same mounted cavalry into play against the machine guns and barbed wire trenches of the other side.
The public's fascination with Einstein, it continued unabated. But Einstein could feel, he could sense that the community of scientists no longer held his work in high regard. Niels Bohr, a friend and one of the founding fathers of quantum mechanics, lamented publicly that Einstein had turned to working on alchemy.
I am generally regarded as a kind of petrified object, rendered blind and deaf by the years. An old chap who is exhibited now and then mainly as a curiosity because he doesn't wear socks. It is a strange thing to be so widely known and yet to be so lonely.
March 15th, 1955, Michele Besso, remember that's the friend who helped Einstein think through the special theory of relativity 50 years earlier. Besso dies. Einstein consoles Besso's widow with a poetry born of an intimacy with time that few had ever experienced.
And now he has departed this strange world, a little ahead of me. This means nothing. To we convinced physicists, the distinction between past, present, and future is only an illusion, however persistent.
A month later, Einstein lays in a bed in Princeton Hospital, and as dusk drifts to night, he closes his eyes.
All the years of anxious wandering in the dark, with their intense longing, the intense alternations between confidence and exhaustion, and the final emergence into the light. Only those who have experienced it can understand it.
No one else had or has experienced it. Our species has surely produced great scientists who've taken on great challenges to achieve great things. But Einstein's radical assault on the most basic elements of experience, space, time, matter, energy, gravity, all waged by one lone mind wrestling with reality, well, that was a singular achievement. And yet it is in that singular achievement that we recognize the depth of the human drive for coherence, for unity. It is within the singular that we see the capacity of the human mind to lift itself above the ordinary and catch a glimpse of the transcendent. And it is within the singular that we witness the power of the human spirit to rise above the all too real concerns of life on planet Earth, and even if for just a moment, to stretch to the stars.